Today we want to take a look at how to deal with limits in trig functions. Let's take a look at question number 1. We want to find the limit as x approaches positive infinity of the cosine of pi x all over 4 minus 6x. So what we want to try to figure out what to do here is how are we going to find the limit of the cosine of our function pi x over 4 minus 6x. Let's split it up as the composition of functions. Remember that if the limit as x approaches c of g of x is L, and if the limit of f is continuous at L, then the limit as x approaches c of f of g of x is going to be f of L. Well, that kind of seems confusing. What that means for us is that if I have a composition of functions, I can take the limit of the inside and then apply that function on the outside to it. So let's go ahead and do that. We're going to take that function, the cosine, put him on the outside, and then we're going to apply the limit to our function on the inside. The limit as x approaches infinity of pi x over 4 minus 6x. We know how to find the limit as x approaches infinity. We learned this yesterday. In order to do that, we have a rational function. The degree of my denominator is x to the first. So that means I'm going to multiply top and bottom by a 1 over x and 1 over x. So when I do that, my cosine, of course, is going to stay on the outside. And then I'm finding the limit as x approaches infinity of pi over, I'm going to have a 4 over x minus 6. Well, as x approaches infinity, we know that any constant over x is going to approach 0. So that's going to leave me with the limit as x approaches infinity being equal to pi over negative 6, or a negative pi over 6. So I'm really finding the cosine of a negative pi over 6. Negative pi over 6 is the same thing as 11 pi over 6. My cosine is my x-coordinate. I'm going to go forward the further amount, and that would be a radical 3 over 2. Now, we aren't going to always be able to split our problem up as the composition of functions. If I look at 2 and 3, we're going to use what's called the squeeze theorem. So let's look down at the bottom and see what the squeeze theorem does. Our squeeze theorem says that if f of x, g of x, and h of x are continuous, with f of x being less than g of x, which is less than h of x, so notice g of x is being squeezed in between f of x and g of x, and if the limit of f is L and the limit of h is L, well then the limit of g would also have to be L. So if we take a look at this graphically, here's my greater function. So here's my h of x. Here's my lesser function, my f of x. And let's say that here's our point, our x-coordinate of A. So at A, h of x is greater and f of x is less than. And let's say that there's some g of x, maybe some function that looks like this. Notice that it's being squeezed at A. So if g of x is in between the two, and the limit of h is L and the limit of f is L, then at A, the limit of g has to also be L. So let's use this idea to figure out questions 2 and 3. If I ask myself for question 2, what do I know about the cosine? I know that the cosine of an angle has to exist in between -1 and 1. So I'm going to start off with a little inequality. -1 has to be less than or equal to the cosine of x, which has to be less than or equal to 1. I also know that I can multiply an equation or inequality, all the parts by the same thing. So since my x is approaching infinity, I'm going to choose to multiply everything in this inequality by 1 over x. And so if I do that, I now have a negative 1 over x is less than or equal to the cosine of x over x, which is less than or equal to 1 over x. And since the limit as x approaches infinity is what I'm looking for, I know that the limit of a negative 1 over x is going to be 0. And I also know that the limit of a positive 1 over x is going to approach 0. So that's going to tell me that the cosine of x over x has to be in between 0 and 0. Therefore, its limit is also going to be equal to 0. So the limit as x approaches infinity of the cosine of x over x is equal to 0. Same idea, let's go ahead and choose this squeeze function to find the limit as x approaches 0 of the absolute value of x times the sine of 1 over x. So again, I'm going to start off and I'm going to ask myself, what do I know about the sine of an angle? I know that the sine of my angle has to be in between positive 1 and negative 1. So I'm going to start off with an inequality that negative 1 has to be less than or equal to the sine of my angle, which is 1 over x, which has to be less than or equal to 1. Now, what happens if I take the absolute value of my sine? Well, if I take the absolute value of my sine, now the absolute value has to be greater than or equal to 0, so that's going to change this, that 0 is less than or equal to the absolute value of the sine of 1 over x, which is less than or equal to 1. I can multiply all parts by the same thing. I can multiply everything by 5, or 1 over x, or in this case, the absolute value of x. So let's go ahead and multiply everything here by the absolute value of x. The absolute value of x times 0 is 0, which is less than or equal to. Absolute value of x times the absolute value of the sine of 1 over x is now going to be absolute value of x times the sine of 1 over x is less than or equal to 1 times the absolute value of x is the absolute value of x. If my x is approaching 0, then I apply my limit as x approaches 0. Well, 0 is going to approach 0, and the absolute value of x is also going to approach 0, which shows me that when I squeeze, my absolute value of x times the sine of 1 over x, if it has to be in between 0 and 0, my limit is going to be 0. Using the squeeze theorem, this is how we prove our true rules on the backside. If we're finding a limit as x approaches infinity, or something strange like x approaches 2 or 3, or maybe, for example, number 1, our x is going to approach a positive infinity, we want to either take a look at applying a function to a function like number 1, or the squeeze theorem. But most of our problems are going to be like the problems on the backside, and that is that our limit as x approaches 0 of some sine of angle x over that x is always equal to 1, and the limit as x approaches 0 of 1 minus the cosine of some angle x over x is equal to 0. And we'll take a look at those problems next.